video of any end?
Please start, Chris. It's ready here.
Right, cool.
Okay, hello. I'm Chris, president of the newly established Oxford Physics Club. And the lecture today is going to be about Saturn's plasmapause boundary, based on my summer project at MSSR Mural Space Science Laboratory. And a nice picture of Saturn for the beginning. So to start off, I would like to discuss what actually is the magnetosphere, where does it come from, and what is the location of that within the study of the solar system. So firstly you have got the Sun, out of which you've got a lot of energetic particles flowing, being blown in all directions. Mostly these are protons, electrons, so that it is electrically neutral. And the composition is just like the composition of Sun, so you also get some metals, etc. Velocity of the wind at the surface is about 400 kilometers per second. It's enough because even though the escape velocity is 600, then there is an end of the tail of the population to escape from the Sun. So it's roughly 400 kilometers per second, and all that is blown away. Plus, you have got the dipolar B field, which sometimes stops being dipolar, because it is dipolar only during the most active moments, so like during the maxima, whereas during the minima it reorientates, and then it stops being dipolar. But overall, because Sun rotates once every 30-something days, it drags with itself entire B field, so it actually looks like something called Porcus spiral or something like that. And these B field lines are just dragged away all the way into the interplanetary region, into the interplanetary part of the solar system. And in fact, as you've got the Sun, and it obviously is located somewhere within the galaxy, and this part of the galaxy moves about 250 kilometers per second within the within the distance. Actually, it's the other way around, but it doesn't matter. Because it radiates something, you got the bubble, which is being blown away, called heliosphere, and all the planets are roughly in that region. So that within the planetary region, you can quite easily think about the space as not being clearly a vacuum, but actually being filled with particles, being filled with the magnetic field. The magnetic field being very weak, roughly it was 4 nanoteslas or something like that. Yeah, it's 4 nanoteslas, as compared to Earth's magnetic field, which was roughly 30,000 nanoteslas at the surface. And because you have got the plasma being blown away from the Sun, it carries with itself the B field, since it is conductive. Plasma is conductive because you have positive and negative charges, it's ionized. So you get the B field lines being stretched in all directions, and basically all those planets revolve within the B field lines, which actually causes all the phenomena that I'm going to describe. And even though the planetary B field, if it was not rotating, not interacting with the solar magnetic field, with the solar wind, would be something dipolar, just like a bar magnet. You would get the B field lines like that. Then, since you have got this solar wind with about 400 kilometers per second and an interplanetary magnetic field coming a long way from the Sun, then it actually gets squeezed here, so that it's not that far, but actually is squeezed in that direction and elongated in that direction. And this is exactly what creates this shape visible on that plot. Then Saturn is just like any other planet, so you still get all the general features. So Sun is to the right, you've got the solar wind blowing from the right hand side, and all that would correspond to the boundary of the magnetosphere. There is a caption somewhere. Yeah. This would be the bow shock, the shock due to the boundary of the plasma confined to the cavity of the magnetosphere. Then we've got magnetopause and all the interesting features of the ring current. But interestingly, this is a very recent magnetohydrodynamic simulation, MHD. And because the hydro bit, it actually looks just like the turbulences in the eddy flow around the cylinder. It's just like having a planet inside the water with some ink or whatever. And it turns out that the plasma behaves just like this kind of fluid, which is quite amazing. But we have noticed that only recently, because up to about 80s, people were thinking that the B-field lines is something very solid and that they would get stretched indeed, but that this would be much less dynamical system. And it actually turns out that it is a hugely dynamical system with all this stretching, with a lot of current systems, with a lot of magnetic field lines being frozen into the plasma. Here you can see those magnetic field lines. And I should mention that because you treat it as a collisionless plasma, therefore the particles only travel along the B-field lines. So effectively you call it a frozen approximation, Alphen approximation, so that the particles carry themselves along only the B-field plasma. And interrupt me whenever you don't understand something, because I want to make it understandable for everyone. Yeah.
Could you explain again why the B-field lines get elongated? Because I didn't get that.
Oh yeah, that's essentially due to the pressure of the solar wind. Because you have got particles carried along the B-field lines. As the particles get pushed by the pressure, they also carry along with themselves the B-field lines.
Well, why?
Why?
Why do they carry B-field lines?
Because they are frozen into the B-field line. This is the approximation, the Alphen approximation. It is a cold plasma, and it is frozen into the B-field lines. Explanation why it is actually frozen would be about 2 hours of lecture. And I refer you to Kibelson and Russell. It's a good textbook explaining it. But actually it turns out from those magnetohydrodynamic equations, which are an analog of Maxwell's equation, but for a plasma. And this is exactly summarizing what I was saying, that the general scheme, sorry for the answer, but it would be too long to actually explain properly, and I don't remember all the equations, because the starting point of my summer project was that you assume that this is the case. You don't actually investigate why. But it is a good question. I have to look it up. And this shows you magnetospheres of all possible planets in the selection of planets in the solar system. And it shows you that basically the features are exactly the same, but scale is massively different. So Mercury, being very, very close to the Sun, has got magnetosphere being squashed very, very close to the surface. It's like one radius. And actually, if there is a coronal mass ejection, it can push the plasma, it can push the magnetopause onto the surface of the planet. So effectively, you don't have any protection whatsoever, because otherwise all the particles would travel along the B-field lines and hit the northern and southern pole and create aurorae ovals. Exactly the same happens in the Earth, but the scale is bigger because it's further away, so you don't get so much squash. You can see that the front of the magnetopause here is about 1 radius, and here it's about 10 or more radii. And then you go to Uranus-Neptune system, and the biggest ones, Saturn and Jupiter, effectively. The Jupiter one is huge. The magnetosphere in general is one of the biggest coherent structures of the solar system. Structures that can actually be considered as one structure, just like the heliopause that I mentioned. This is one structure, and magnetosphere is the biggest other structure within the magnetosphere, within the heliosphere. So it's quite a big deal.
Why is it so big?
You could think of it as just the balance between the pressure of the solar wind and the plasma, which is being driven not only by the B-field lines. B-field lines are just there, so they don't actually do anything. If say you didn't have any solar wind whatsoever, you just had a rotating planet to produce the B field, then you still have got some plasma. So what you would get in a perfectly symmetrical situation would be something that you sort of get in case of Jupiter. So you would have a planet which is rotating. You've got the B field lines, but because of the plasma in the system, I mean, if this was Earth, then it would not be actually bounded by anything. So what I'm saying here is that this is the boundary where the pressure of the B field driven system is exactly the same as the pressure of the solar wind, which is why you get the shock, the bow shock. And if you didn't have that, you wouldn't have any boundary, so it would stretch to infinity. It would just decay in some exponential way. I mean, yeah, the B field of the Earth decays in 1/r², just like the E field, because it's the same thing. And this was in case of Earth, where you'd have no plasma at all. Plasma, is everyone familiar with plasma actually? Because I mentioned, but it's actually very trivial. It's just some electrons and some protons. Basically ionized gas. Ionized gas is plasma.
But is it overall neutral?
Overall it is neutral, okay. But locally, if you get
it's just separate.
If you get an ion, if you chuck in some positive ion, then the electrons would tend to surround it, and they would shield it from being affected by the rest.
Right.
So you get something called Debye radius, which is the radius of interaction. How far does the plasma know that the ion exists?
Right.
Overall, it is neutral because plasmas are a huge field of research. I mean, people would tend to think that plasma is just a very hot and dense matter, but it can equally well be very cold and diffuse, just like the solar wind. And this is the kind of plasma that I'm talking about. It's very cold and diffuse. But then when it starts to interact with the solar wind, you get quite a lot of friction, and you actually get to high energies due to the fact that even though the velocity overall seems to be small, then remember it's just an electron or proton. So the energy would be like 10 to the 4 electron volts.
Oh, okay, so you're saying for a plasma it would be about 10 to the 4 EV is
Yeah.
the energy, okay.
Yeah. It doesn't have to be that. I mean,
But typically in this situation.
it's enough to have 13 EV because then you ionize hydrogen.
Okay.
So it's anything more than 13 EV per particle, per electron basically. But if you have got this plasma, those particles, then this system is actually filled with them. And surely if they are frozen in the B field line, then because there is a drag with the atmosphere of the planet, those particles are carried along. So as it rotates, those particles are also carried along with the atmosphere. And because the particles are carried along, the B field lines are also carried along. But depending on the velocity of the rotation, it's going to be either a spherically symmetric situation, or there will be much more centrifugal force in the equatorial region than in the polar region. So you will get a stretching like that. This kind of symmetrical disk in both sides of the planet. As it rotates, you would get a stretch of B field lines, just because you get a stretch of the centrifugal centrifugal stretch of the particles. And this is exactly what we observe in Jupiter. It's not clearly visible here, but well, you sort of can see that this spike here is not visible too much on Saturn and not at all on Earth. This spike here corresponds to the so-called magnetodisk, and this is exactly the disk of particles which are centrifugally driven outwards, and they carry along the B field line, and therefore they get stretched and produce this kind of magnetodisk. It's a very interesting structure, but it's on Jupiter, not on Saturn. Saturn is something in between. That's a nice picture. Again, you have got some Mercury, Earth, yeah. Topologically, it's all the same, but as I've shown, the size, the scale is vastly different. And let me show you the size, relative size. I mentioned that it was huge. So actually, if you were to be able to see it on the night sky, this would be the size of the magnetosphere of Jupiter. It's really huge. Hundreds of thousands of kilometers. But, because you can't see it, you have to, well, you can't see it in the optical, and it doesn't emit too much, so that you do detect on the radio those waves that when the particles hit the aurora. But then, otherwise, when you're within the systems, those particles are just traveling. They are not traveling fast enough to emit any kind of synchrotron radiations or anything. So you don't really get too much emission, and it's very hard to detect them if you're just doing Earth-based observations. Which is why we have to send a probe, and we have sent Cassini, which arrived on Saturn in 2004. But let me still explain what is actually the difference between Earth, Jupiter, and Saturn when it comes to this kind of system. So these are just two definitions from some papers, but they both agree with what I previously described. A plasma pause on Earth represents the last closed equipotential of plasma flow around the planet, which means that this is the last closed region which is dominated by the plasma and is not affected hugely by the solar wind. And the other is that it is a boundary that separates a cold, dense, co-rotating plasma in the inner magnetosphere from a hot, tenuous plasma that floats sunward through the outer magnetosphere. And that corresponds to that picture that I've drawn before, that when you've got the interplanetary field and the planetary field, it doesn't work, and the planetary field and the planet, then having the solar wind in that direction and the interplanetary field, you've got the region which is dominated by the solar wind all the way around here. This is where the reconnection happens, and this is something hugely interesting which I will also describe. And then this would also be the end of that region. Outside of that, there is not much plasma, and therefore the solar wind drives the particle. So it also means that if the particle gets here, it would be more likely to be carried away by the solar wind rather than staying in the system and going into the pole. And because you get different amount of plasma in the system, this is the most important parameter that defines the size of the plasma pause. It might be either tiny, like on Earth, or huge, like on Jupiter. And the vastness of it corresponds to the magnetodisk that I described. And Saturn is something in between. What do we have here? Okay. Sources of plasma. On Earth, not much, just ionosphere. Because on Earth, the moon doesn't produce any plasma. You don't have any other moons that would be able to give you a lot of plasma into the system. So you just get some particles which are left over from the solar wind or ejected from the atmosphere by the interaction of the solar wind. Whereas in the Saturn or Jupiter system, you do have those sources of plasma. In the Jupiter, it's Io, the most volcanically active body in the solar system, with about 1,000 kilograms per second. And in case of Saturn, the main source of plasma is Enceladus, which only gives you about 300 kilograms per second of plasma. May seem like a lot, but quite a lot of plasma is lost into the system because it goes along those field lines, and according to one of the things that I will describe, at some point the the field lines are so weak that they just break, reconnect, those connect here, and this blob is carried away, which is called the plasmoid. So you do lose the plasma, and if you didn't have those moons which are constantly producing the plasma, then the system would not actually be affected, because you would quite quickly lose the plasma. And there is a relevant timescale which connects the amount of plasma to the properties of the planet itself to the rate at which you lose it.
How do they produce plasma?
These are just ionized particles, so in case of Jupiter you just get volcano. It is a volcano, and here it's also a volcano. I mean, I call it a plasma, but in case of Enceladus, it's mostly H2O, actually. It's a water geyser. So you do get a lot of protons and oxygen atoms, highly ionized. And this was discovered quite recently, a few years ago, and they found out that the source of this activity might be quite similar to the source of activity of Io, due to the tidal heating. And Enceladus is on such an orbit that it gets squashed, and then due to that you get quite a high release of heat, and it is exactly the same reason why you get so much activity on Io. But because Enceladus is much further, it's actually covered with ice, and the only way that those geysers could operate would be to release all the water, so the water is heated up and it gets ejected. Whereas Io is close enough to get actually a molten lava, so that the composition of this plasma is different. This one would contain quite a lot of sulfur, whereas this one contains mostly just water. But it's still plasma, and that's what all we care about. Now the most interesting part, which is how does actually the plasma, given that you have got some amount of the system, in the system, and the solar wind, and the B field lines, and the interplanetary B field line, all together act to produce the dynamical system that we observe. And this was only discussed by Danji in '67, and then Vasilinus invented another cycle in '80s, so it's quite a recent thing. I just use nice pictures, because there are so many pictures that it would be pointless to show it on slide, so it's easier to draw. So first and foremost, you've got a solar wind, interplanetary magnetic field, and the planet, and the magnetic field of the planet. Because they are in different directions over here, this is the Danji, the first one, the one that was described, even in the 70s. And it applies to all planets. You get Danji cycle on Saturn, Jupiter, Earth, but in different amounts, with regards to a different circulation, which is called Vasilinus, and I also describe it. So, those two field lines might connect, and as they do, they will look like that. And because they have connected, all the plasma that was flowing along those lines gets freed and follows along those lines into the interplanetary medium. And that's why, if you are on the spacecraft and you are trying to see where does the reconnection come, where does the reconnection happen, and at some point you start seeing much less particles coming from that direction as from that direction, you know that this is something called open B field line. We know that in nature they are not open, all of them have to be closed somewhere, but this one closes so far away, almost at infinity, that you call it open locally. And then
would they connect when magnetic field strength of the sun, of this line from the sun will be the same as the line from the planet?
They are connected, yeah.
But only when the strengths are equal, or not?
They connect just because they are pointing in opposite direction.
But the B field from the sun must be very small. It's so far away.
It is very small.
And from the planet it must be stronger.
Well, it's not, because it decays as 1 over r squared. And this is not closed. This is like 40 Saturn radii. So as it is connected, it just gets pushed by the solar wind. It travels along here, and then it joins this one here. And because they are now traveling in the same direction, they connect. And then they travel here. They are attracted.
I think what Chris was trying to ask is, at the point of reconnection.
Yeah.
Sorry, that's where the field strength is not. It's not only that it's in the opposite direction; they're of the same size, so that they cancel.
Yeah.
So if you look at the other side,
Wait.
right? If you look at where you've drawn the opening.
That's pointless. They have to be in the They have to be in opposite directions to connect. Oh yes, because no one has corrected me that this one is going in that direction. Because it was like that.
Well, you drew it before you rubbed it out. I think it was okay.
Yeah, so this one is going like that. Because if this one connects with that, then it's now going in that direction. And this one is going in that direction. And same here. Yeah, so that's close. And it actually has got the same polarity as the original planetary field. And it connects here. And all the plasma that has been trapped along those lines now first goes back into the system, and B travels along the newly closed lines, hits the polar region, and creates aurora. And that's exactly the mechanism of aurora creation in the Earth system. In the Saturn system it's sort of similar, but there is also another cycle called Vasilinas. And essentially the Vasilinas cycle is just the centrifugally driven plasma which stretches those lines so far that exactly what I described happens, and those lines connect here and those separate, forming a closed loop, or maybe some additional magnet. I didn't look into the detail, but they would carry along some plasma, and this would reconnect. So what actually happens in the big picture is that you lose some of them into the solar wind due to the Danji cycle, and you lose some of them due to the Vasilinas cycle. And the strength between the two is what actually characterizes the system. Another interesting thing, well, I found it interesting because this actually is the physical understanding of what's going on, not just nice picture, is where do the currents come from, the electric currents. Because if you have got B field, the curl is non-zero. What was it? Curl B is mu naught J or something like that. So you will get some current just from the fact that the curl is non-zero because they are curved. That's a bit more complicated, but I can actually use, well, I can just draw one picture, and then I will show, I will do the demonstration. So what was it? That direction and that direction. That's the most important current. We should expect in this kind of system, just because the B field line is curved like that from Ampere's law or from any other standard physics law, and this is called the ring current. And the ring current exists in all systems, in particular on Saturn. I've shown it here on one of the first images. Yeah, this one. This is the current that comes just from the fact that the field is dipolar and it's curved. You get it around all planets. Then, because you get some plasma in the system as well, and as I've shown, the system is rotating, and the plasma is being frozen into the B field line. So as I mentioned, if the plasma gets dragged, then also the B field lines get dragged. So in 3D, what happens is that if I were to imagine this as a cross-section, it's like a sheet of paper. So it's just a cross-section through the planet. Well, this is what I've been drawing all the time. But now, this cross-section curves like that. And now the B field lines follow the same pattern, but they have been pushed in that direction because of the rotation in that direction. That's just like having your B field lines on the sheet of paper, and then this plane gets curled. And all of those get curled a lot against the direction of rotation. And then, just because you get this turning, when the angle between the old position and the new position is 90 degrees in the maximum elongation, then you do get outward J. I mean the outward current. In that direction. And then you get a force. So actually it's hard to draw, but what I'm trying to describe is that having a sheet of paper originally like that, and then bending it like that, you will get the current which is trying to restore the position of those lines to the original ones in that direction. So it's along the old one. And this is basic, and because this current would flow outwards along the old meridional plane, and this happens in all positions along the entire planet, you actually get something that flows out from the inside to the outside of the planet in the equatorial plane. So you get current that's not only flowing as a ring, but you also get a current which is flowing outwards like that. But then it has to go somewhere. It cannot just end in vacuum. So it will follow those lines and hit the North Pole. And then it follows sort of surface or the upper layers of the atmosphere and reconnects. And this is how it looks like. Same in this part. And it also contributes to the strength of aurorae. Another thing is the azimuthal B field. And azimuthal B field is just because here, in that region, I'll draw a better picture. Because I spent some time trying to make it nice. You have got a B field, outward upward current, the B field line, which has been extended a long way, and you hit back the North Pole. And exactly the same happens here. So you've got B field line, current, extended B field line, and going back. And essentially it goes in that direction, just like the B field line. And as you see, you've got quite a curling of the B field line here. And you could think of it just like having a solenoid. And a current flowing, then you would get a B field in that direction through the solenoid. And because this curling is just like that, you also get B field all the way along here in that direction. So it's a very interesting system because you get the B field interacts with plasma, gets curled. This curling produces forces which induce the current. Then the current, just because it's curled, because it follows the B field lines, produces additional B field. And this B field also induces some currents. So it's like an endless loop of currents which are less and less intense. And actually, you could start from those currents, assuming that there is no B field, and you would trace it back, and you would get exactly the same B field that you have started with. So it's quite a neat technique. And this B is the azimuthal component of B field. And the measure of B phi, the azimuthal component, gives you a measure of the current flowing in the system. So the stronger the B field is, the more current you have got flowing in this region, because this is the strongest current just after the ring current. So basically, the more azimuthal B field you have, the stronger the current is. And the stronger the current, the more plasma you have in the system. So it's also proportional to the amount of current in amount of plasma in the system, and the strength of the total B field line. I only mentioned this B phi because it was one of the things that we measured using Cassini. You ignore all the other components. You have got B, R, theta, phi, and those R, theta are not really useful for anything because they all interact with other components of B, whereas the azimuthal B field comes directly just from this cycle, which is why the azimuthal B field is so interesting. Okay, so now I guess it's the best moment to jump into what we have been actually measuring and what is Cassini and everything about the spacecraft. So that's Cassini. This picture was made when it was still in the assembly room. Ignore everything. The caps is this small box here. This is the instrument that I was interested in. And this is what the box looks like inside when it was assembled in the Muller Space Science Laboratory where I was working.
Do you have a size scale for both of them?
The scale?
Yeah.
It was a box like that.
And the spacecraft would be
Spacecraft
10
was
meters, 20 meters?
that would be the size of the person. I remember a few of that. It fits into a Saturn V.
A Saturn V rocket?
Yeah.
Okay. Do they still use
Did
this?
they use Saturn V
is
or
not
Ariane?
Ariane probably. Ariane 5.
Yeah, because Saturn V is huge.
The new, yeah.
But Ariane is still big enough. This is the... So having this spacecraft, we obviously did quite a lot of orbits. Since 2004, it was orbiting Saturn in all possible directions, on quite an elongated orbit. And these are the moments that I was interested in, because as I described this region, the plasmapause, it has got the properties of boundary. So what I'm interested in is just the crossing of the boundary. And it turned out that because the plasmapause itself is a region where you still have got a lot of plasma, which is driven by the B field, and outside of that you don't get a lot of plasma, there is a huge increase. So if here it would be time, and this would be log of energy, then the actual difference of energy would be from 10 to the 4 to just few electrons. Sorry, the number of particles, this must be number. And energy would be just colored with red, green, whatever. I'll show you the picture later on. But the idea behind those plots, which are called the spectrograms, is that you've got a number plotted in the vertical one, and horizontal one represents the time. And as you are flowing through the system, you hit a boundary which is increased from about 10 to 10 to the 4 electrons per cubic centimeter. It stays roughly constant when you are flowing through the plasma sphere, and then as you exit, it again drops down. And you can quite easily mark the beginning and the end. And from all those passages of like hundreds of passages of spacecraft around Saturn, I was able to find about 82 data points which actually corresponded to this kind of sharp boundary. Because otherwise, if it was, say, flowing at an oblique angle, like along the plasmapause, then you wouldn't get sharp boundary like that, but rather some kind of fuzzy patch, and you wouldn't really be able to tell where actually is the boundary, because then the population is not so squeezed in the time domain, it's quite extended in the time domain. So I would have to integrate over much longer time, which would decrease the accuracy of the time determination. So these are the first results, which were actually not from my paper, but from Gernet et al., on which I based my analysis. And this is what I have drawn here. Well, that's actually frequency, but the Langmuir probe shows you the density, which is the number density. That's the time, and this is 10 to the minus 4, that's a normalized scale, but it's exactly the same ratio, 4 orders of magnitude, from the bottom to the top. And the boundary crossed here, it crosses just like on my previous illustration, from south to north. Mine was from north to south. And then this plot shows you the B field, and as you can see, the black one is radial, the red one is theta, so it's like tangential, and the green one is the azimuthal one, which we're interested in. And those are pretty featureless, but you can actually see that in the azimuthal component you do get a spike when you're crossing the boundary, and this corresponds to those current systems that I described. And I did an analysis of this particular day using the same data, but with different program that was written by scientists from the Cassini team. It took them 2 years to write this program. It's called full res display, and what you can see here is exactly what I described here. So you get time on that direction increasing from left to right, and then this is the amount of particles, and energy is plotted with color. So you do get a huge spike in intensity of electrons here with bigger energy. Then you are flowing through the plasma sphere, and then you exit. And this corresponds very well to the azimuthal B field line plotted here. I wrote the program to plot that to check if they got it right. And these plots are just like having the spacecraft itself had spacecraft like that. It had those spikes, 8 of them, 8 anodes, which are pointing in different directions. So as it was flying through the space, it could also identify whether electrons were coming from here, here or there. And they were separated roughly like 25 or something degrees. It was not even, but you did get a distribution. And then between those anodes you could integrate. and that's where these plots are coming from. So it's not 280 along B negative and B positive. And the interesting thing is that you can see that there is a distribution along some direction. There is a preferential direction from which the electrons are coming, exactly when you're crossing the boundary. And in fact, you would expect that the direction should change as you are exiting the boundary, according to the mechanism that I described before. And initially we thought that this is quite a nice thing, because if you do get the B field and you do get those opened field lines, which corresponds to the fact that the lines have been opened to the lines have been opened to the solar wind. So you lose the plasma from this direction, and you don't get a lot, whereas in here it might be closed, so you do get plasma. And that's why one direction would lack the electrons, whereas the other direction would have quite a lot of them. Yeah, that's right. But actually we found out that it's just either systematic error, experimental error, or just a sheer luck that it agrees for this boundary, because it doesn't agree for another boundaries. And so we thought that perhaps it requires further investigation. That's a zoom in, what I've shown. And because these anodes also rotate like that, then you don't get a full coverage, but only it stops. It's about 100 degrees. I have to skip to my paper. This one. To show you what has been done in terms of pitch angle analysis. Because these are the boundaries that I found in the data. I found many of them. I found 82 of them amongst more than 1,000 spectrograms that I looked through. All of those come from 2008, which seems to be a particularly good year because the crossings were perpendicular, and in all the other years the crossings were not perpendicular through the plasmapause. And we have chosen the best boundaries, actually the same that have been described by Garnett, to do the pitch angle analysis, the pitch angle distributions. These are the additional boundaries that he has investigated, and we have also investigated the boundaries corresponding to those dates. So I looked at those pitch angle distributions second by second, and tried to see at which moment do you get increase in electron population. But because it's, as I said, not particularly well connected to the fact whether you have